at infinity? All right. And so we've dealt with ratios. We know how to deal with ratios now. And the thing that you want to remember that's very useful is that when you're dealing with ratios and you have complicated expressions in the denominator, the denominator may be, for example, like a power of x plus a root. You can kind of divide and conquer. You can look at each term in that expression and pick the leading term in that part. And then you can compare all the leading terms together. So in other words, if I had the denominator something like this, the limit as, well, I'll write it here since I'm making a video anyhow. So if I had something like the limit as, we'll say, t goes to infinity of t squared plus the square root of t to the fifth plus t cubed over the square root of t plus 1 plus the square root of t squared plus 8. I look at that, wow, no clue how to do that. But I just break it down. I say, okay, what is the principle? The principle is I'm interested in the leading term. I don't know what it is here, maybe, right at the top of my head. But what I do know is that for this part of the expression, this is the leading term. So then I would just say, okay, let's ignore him. Let's ignore that t cubed. Then I'm going to have to compare these exponents, right? So this is t to the 5 over 2. So this is t to the 5 halves, right? And so who is the leading term on the top? This guy here, right? 5 halves, 2.5. So he's going to be my leading term. Here I'm looking at two roots, and they both are of the same order. They're both square roots. So I can just look at these and say, which is the highest power here? T squared. What's the highest power here? T. This guy obviously wins. You can look at this after a while and not have to do a lot of work. So I have two roots. So what I'm going to do is pick out the leading term of the root. So this guy wins. T to the 5 halves over the square root of t squared, which is t. That's going to be an infinite limit, because the exponent on the numerator is higher than the exponent in the denominator. So this is kind of a useful thing to know to break things down. Any questions on that? So the one thing, and so this same sort of thing applies, you know. I have a root, but the same principle applies. Take the leading term on the top, leading term on the bottom. It's exactly the same sort of problem. We're always taking the leading term on the top, the leading term on the bottom. Then we'll take the square root. We'll worry about that afterwards. So ratios shouldn't be too hard, because all you do is you're just always picking out the leading term. That's it. And then you're just comparing them. Now, these are the harder ones. So a little bit of a word about limits at infinity when we don't have ratios, okay? Some of these can be rectified, but for example, suppose I have two functions that as I look at the limit of infinity, they're both infinite. We'll call them f and g, okay? If I look at the limit of the sum, it's infinite. We can't remedy a situation where we have two infinite limits and we sum them. That's obviously going to be infinite. So when we have problems like the limit as x goes to positive infinity of f of x plus g of x, that's always going to be infinite. There's never any exceptions. If two functions are both growing without bounds and you add them, it's worse, right? They're growing without bounds even more. So that's pretty obvious. But when we look at the difference, sometimes we can remedy it. But the only case that we know about right now is, so sometimes we can fix this up. Kind of like 0 over 0, right? Sometimes we can fix it up, sometimes we can't. But the only time when we can deal with this, the only thing that we know how to do is situations where one of them, at least one of them, is a root. Okay. So when we have something like this, we're going to need one more condition, that either f or g is a root. And when we have that, square root. And when we have that, then we can try to do, rationalizing the numerator in this sense, in this case. And so we talked about this last time, but I just wanted to go through this one more time. So this is when we're going to rationalize. And that's what we're doing here. We're taking the conjugate and multiplying it over itself. And that way we're getting rid of the root on the top. But notice it only works if that's negative, because on the bottom, what am I going to have? I'm going to have positive, right? So when I actually do this, it's going to be x squared plus 1 square root minus x times, and we did this last time, but I'll just write this out again one more time. Square root of x squared plus 1 plus x but I have to have that plus on the bottom. If I had a negative on the bottom, I'm not going to be able to get anywhere, okay? So here I'm going to get rid of that squared, and here what's going to happen is I'm going to have two things that are both going to infinity being added. And that's good, because 1 over infinity, I know how to deal with. That's going to be 0. So that's the rationale behind that. Whenever you see a root and you don't know what to do, almost always the right answer is rationalize. It's not obvious. Okay. If I had it in a ratio, like the one that I just showed you a second ago, you could probably deal with this one. This one's not hard to deal with. Okay. But if it's a new situation, something where it doesn't compute, okay, you're not going to be able to get the leading term like that last one, then we have to do something else. And the only thing we know how to do with roots is rationalize. That's the only trick we have with roots. So any questions on handling limits at infinity? All right. A couple of limits that we should know. One really important function is the exponential function. Notice the exponential function is the problem e to the x. There actually is another function called the general exponential function. That's a to the x, for any positive number. So if you have bacteria, for example, you're looking at how they multiply. A is 2, right? Every time period, they're going to basically double it. Okay. Here, e is just a number, but what's important about e isn't so much its value. It's kind of one of those weird numbers like pi. So it's 2.71828, blah, 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 blah. Goes on forever, never repeats. It's all these weird numbers. But the only thing that we really care about, that's really important for us, is the fact that it's greater than 1. That's the key thing. Because when you take any number greater than 1, and you raise it to a power, as you make that power bigger and bigger, what happens to that number? It gets bigger and bigger. And if you don't have good intuition on e, and most people don't, because we don't work with this number, it's a weird sort of number. Just think about any number greater than 1. Think about 2, right? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. By the time you get up to 2 to the 20th, you have more atoms than there are in the known galaxy. It's a number that really increases quickly. So you can use that as kind of a benchmark, all right? So what this means is that as x goes to infinity, this tells us that e to the x also goes to infinity. And that's why the function looks the way it does, right? So this describes any sort of growth for a short period of time. Growth of populations, growth of, virus, anything like that, spread of a virus. It tends to follow this pattern for a short period of time. But we're interested in this limit. I'm interested in the limit as x goes to negative infinity of e to the x. So let's think about this for a minute. As x goes to negative infinity, what's happening to e? Well, e looks like e to a negative large number. Okay? This is what e looks like. X is getting larger and larger in magnitude, but negative. So this is looking like e raised to a very large number that's negative. And I'm going to write this as, I don't like negative exponents. How do I get rid of negative exponents? 1 over e. Excellent. So I'm going to say it looks like 1 over e to a large number. But now, can I use this fact right here? As x gets really big, e looks like e to a really large number, which goes to infinity. So this looks like, I'm going to write something that's not quite correct mathematically, but I'm going to write this. It looks like it's going to 1 over infinity, which is what? 0, right. As you go to 1 over a number, it gets larger and larger and larger without bound. This limit's actually 0. That's what that limit's going to. And so this tells us this portion of the curve. As x goes to minus infinity, e to the x goes to 0. Now, we don't usually use this form because usually the variable is time. And we don't think about negative time, okay? And we all wish we could go back, right? But really don't have negative time. So we sometimes rewrite this in a different way. And I'm going to claim that these two things are actually the same. I'm going to claim that the limit as x goes to negative infinity of e to the x, which is 0, is also equal to the limit as x goes to infinity of e to the minus x. Okay? And, nothing up my sleeves, right? Just kind of think it through. What's happening as x goes to infinity? Well, I'm going to write this as 1 over e to the x. So as x gets really large, e to the x is getting larger without bounds, so 1 over it's going to 0. And you might say, well, I knew that, that's not a big deal. But the point I want to emphasize is that very often, when you're evaluating a limit and you're having trouble, it's not a bad idea to change the variables. Okay? For example, you might not like limits going to negative infinity. You might say, I don't like looking at x goes to negative infinity. How do I change that? Let's just make a change of variables. Okay? Suppose he said, I don't want to do this limit. I don't want to work with negative infinity. I don't like thinking about this. Why don't I just make a change of variables? T is equal to minus x. Okay? Now, as x goes to minus infinity, what's going to happen to t? Where is it going to go? What do you think, Rashad? Help us out. As x goes to negative infinity, it's getting really large and negative, right? If t is the opposite of that, what's that doing? It's a negative of a large negative number, so what? It's going to become a large positive number. So as x goes to negative infinity, right, t is going to positive infinity. Now, so what's the benefit of this? Well, let's go ahead and rewrite this limit. So now I'm going to put t in here. I said as x goes to negative infinity, t goes to positive infinity. And I'm going to make this change of variables, right? Instead of x, I'm going to put in minus t. And this one looks probably a lot more familiar if you do physics. All right? I know that that's going to be 0, because that's the same as this right here. These sorts of functions occur a lot in any sort of motion where you have damping, where you have friction, for example. You see that things will decay, the velocity will decay. When you drop a heavy object in a viscous fluid, okay, you get to the terminal velocity, you approach the terminal velocity the same way. In aerodynamics and in flight, these exponential decay functions are just ubiquitous. They're all over the place. Okay, and I want you guys to be safe pilots and aeronautical engineers, because I don't want it going down when I'm in the plane. So let's look at this one here. I'm going to rewrite this because it's a little small. So this is the limit as x
goes to 0 with this weird negative sign, e of 1 over x.
Okay, this is definitely a case where I want to make a change in variable. I look at this, have no clue how to do this initially. And just like you guys, I have to puzzle through it. What does this mean? X goes to 0 with that negative sign. What does that mean? Go ahead. What does it mean? You kind of. What does that negative sign mean? It means I'm approaching from the left. Bingo. That's it. I'm approaching from the left. So it means that this x value is always negative, right? This is what it means for x to approach 0 from below. It's approaching 0 from the negative side. So this is getting smaller and smaller and smaller, but it's negative, right? Okay. Now, we're doing limits at infinity, so I'm going to somehow want to change this to infinity. How would I do this? How would I change that to infinity? 4, right? I got to write this down. How would I do that? How could I change that problem to a problem of infinity? 0 and infinity are related, right? How are they related?
Like, you just think about it going to the side.
Okay, but if I want to change that problem to a problem of infinity, how are 0 and infinity related? There's actually a relationship, kind of loosely speaking. 1 over infinity is what? 0. And 1 over 0 is kind of infinity, right? So how could I rewrite this? As x goes to 0 from below, how can I rewrite that as an infinity? In terms of infinity? What would I do? Now, I have a clue. So this is a good problem. What do you do when you come across something that doesn't look like anything you've had before? This doesn't look like anything that you've had. So here's how I look at it. I look at this and I say, man, if this was just e to the x, I could do this problem. Okay? I know everything about exponential functions, right? No matter what x is approaching, I can tell you. If it's approaching a number, I know the value. If it's approaching positive infinity, I can do that. If it's approaching negative infinity, I can do that, right? So why don't I try this? And I don't know, okay? But let me just try this. Let me, motivated by this weird-looking thing and the fact that I like e to the x, I'm going to introduce this change of variables. And I like that because that sure makes my function look easier now, right? If I do that, I'm not going to worry about the limit part, but this looks like e to the t. I can do that. But what's the limit going to be now? What is t going to approach? As x is approaching 0 from below, what's happening to 1 over x? It's getting really small, right? So 1 over x is doing what? Blowing up. And it's staying negative, right? Does everybody see that? This is a little tricky. A little bit sleight of hand. So as x goes to 0 from below, okay, this means that 1 over x is going to negative infinity, so t is going to negative infinity. Does that solve my problem? Well, probably, or I wouldn't have done it, right? But let's just see. T goes to negative infinity. There's my limit. I know how to do that. I have a rule for that, right? As t goes to minus, if I write it correctly, t goes to negative infinity. Sorry. I know that this limit is good old 0. And if you don't like negative infinity, you can make another change of variables. You can say, okay, now let's let x equal to negative t, and then x would go to positive infinity and have e to the minus x. There's more than one way to kind of thing, right?
In your final answer, are you allowed to write that t is going to negative infinity instead of 0?
Well, notice that as x is getting really, really small and going to 0, 1 over x, right, is getting really, really large. So as this thing is going to 0 from below, this is going to negative infinity. 1 over x is getting large, right? As x is going to 0, 1 over x is getting huge. And we have a sign issue because we're approaching 0 from below. So it's not only getting large in size, it has a negative sign. Because of negative thing. Does that answer your question?
Yeah, I'm just having trouble grasping it.
It's kind of tricky. We have to come up with a kind of this little clever substitution. But again, what motivates this is the fact that I don't know how to take the limit of e to 1 over x. So I try to simplify things and see if I can do something with that. Re-express what the limit is.
So your limit is 0. But so what was the original question?
This guy here. And what I've done is I've rewritten this limit like this. And I can evaluate this limit. This limit is 0. But these are the same limits. These are exactly the same limits, making that change of variable.
So why did you change the variable?
I don't know how to do this problem, do you?
We know that 1 over x approaches 0. This is the limit.
But notice you're going through the same thought process. So if you can think it through that way, that's fine. And that's okay. So you can say, okay, as x is going to 0 from below, 1 over x is getting really small and negative. I mean, x is getting really small and negative, so 1 over x is getting really large and negative. So e to the minus a large number is equal to 0. You're going through exactly the same thought process. Okay? Yeah, if you can do that, that's fine. That's good. Yeah.
So the answer to our original problem is 0, not negative infinity?
Well, this is what this variable is approaching. This is what t is approaching, but the limit of this function is going to be 0. Yeah.
So our original typed function, the answer is 0.
It is 0. Okay. Because these two are it's exactly the same. I'll just go back and show you this real quick. This problem is really the same as this problem, where we've taken the limit and we've just rewritten it in a different form, but it's the same limit. Yeah, Ben.
If you don't need to rewrite it for
you don't have to. You don't have to.
Work-related purposes, though, how would you show work for just knowing that 1 over a small number?
Right. So if you want to take your method of doing it, you could say. So here's another way of saying it. You could say that as x goes to 0 from below, x gets small but negative. So 1 over x is basically going to, negative infinity, which means e to the 1 over x is going to be going to a large negative number, and we said that's 0. That's kind of what you're thinking, right? Yeah. And that's good. If you can get to that point, that's good. Sorry? What's small than 0? Negative. Sorry. Small than 1 over that's getting really large and negative. That's exactly the thought process. Yeah. So what is this looking like? Well, this is hard to plot, but you're looking at x, and what I know, if I make this transformations, I know this function kind of looks like this. So the function. Let me think for a second. If I want to plot this, yeah, the function looks like this, and it's not defined at 0. That's kind of a good thing to think about, right? Because what's actually happening is x is going to 0 from above. This looks like e to the 0. No, I'm sorry. Actually, hold on. The function actually looks like this. Sorry. Yeah, the function looks like this. This is a good thing to think about. So let's think about it. We know this part's right. What's happening as x is going to positive infinity? What's happening? Let's think about this. This is actually a good problem. So we know that this part is correct.
what's happening as x is going to negative infinity? 1 over x is going to 0 from below, right? So 1 over x is going to 0 from below. So this is like e to the minus, this is like e to a small positive number. I mean a small negative number. And this is actually equal to 1. So this function is going to look like this. It's actually going to approach 1. As x goes to infinity, x goes to negative infinity, 1 over x basically goes to 0 from the left. As I'm going to 0 from the top, what happens? 1 over x becomes a really large negative number, a large positive number, right? So e to a really large positive number goes off. Which one? Yeah, actually, I want to draw this. Thanks. I drew it from below. I want to draw it from above. Thanks. The function goes like this, and I'm not sure what it's doing in between. Okay, but it's approaching a horizontal asymptote. So the exponential function is always positive. That's a really good point to note. Exponential function is always positive. Thanks. Yeah. I'm approaching 1 here. Yes. No, it won't go below because that's what's a good thing. I should have caught that. Because the exponential function is always going to be it's always going to be positive. Exponential function is always positive. So I approach 0 here. I approach 1 as I go up this way. As I approach 0 from above, 1 over 0 becomes large and positive, right? And what happens is as I go to infinity, well, this is going to approach 1 also, right? So the graph looks like this. As I'm going to x to the infinity, 1 over x goes to 0 from above, so e to the 1 over x goes to 0. This is a big function to think about. I would be a little careful about doing that because the square root, you have negative numbers.
Yeah, but if you put a negative number at the bottom, I found out that it goes up and I was going to correct it on that side of the graph originally. But then, we got that goes from the other way, so it's going to be a line.
I'm not quite sure what you're asking. I'm not quite sure.
2x squared root would be x squared root times, and then e. I figured that out, right? I want to take 1 over x and equal to 1 over 2. 1 over negative 2 is e.
Right.
I dropped it, and that function, and that be okay.
The problem is you're not going to be allowed graphing calculators.
I would have to think about that.
Just graph behind. I'd have to take a look and see. There's more than one way to do the problem. Okay, so it's possible it's right, but I'd have to see. That's not one that I'm thinking off the top of my head. But yeah, let's look and see. Okay, so this is just making the point that limits really correspond to asymptotes. So when you have an infinite limit, it's a vertical asymptote. When you have a limit at infinity, and then it's a horizontal asymptote. When you have a limit at infinity that's infinite, it's generally going to be an oblique asymptote. We're not going to talk a lot about oblique asymptotes. Okay, we're just going to say it goes to infinity. So I'll let you guys read this. There's not a lot. This is just kind of for your edification. Yeah. Okay. So we're pretty much done with 2.6. I'll just let you read the rest of the stuff. All right. We're coming back to tangent lines. And you might say, oh, we've done tangent lines. But there's kind of something a little subtle about tangent lines. how did you define a tangent line? Does anyone remember? What did you say a tangent line was? Okay, so tell me if this is a tangent line. Let's see. I'm going to draw this function. And I'm going to choose this. Is this a tangent line right here? Why not? Are you sure? Here, I'm going to draw this. What if I draw this function here? I'm going to draw x cubed, actually. Very, very tame function, right? What if I want to know about the tangent line at x equal to 0? This is for the function x cubed. Is this a tangent line? Turns out it is. Now, what's so special? Why is it so special? Why would you have the curve? So if you go back to our definition, we kind of gave a kind of airy-fairy definition. We said, okay, it just raises the function and it stays on one side. That's not always true. And so to actually give a good definition, you have to really evaluate that limit, which is kind of like begging the question. You know, we took this approach to kind of figure out how to set the limit. I was saying that. The reason why is we don't deal with functions like this very much. We tend to deal with functions that look a lot more like this. Right? We deal with these nice functions like this. And then we say, okay, we're at a point, and there's the tangent line. We don't generally deal with that. But we want to understand, why are these two okay tangent lines, and this one isn't? That's what we want to figure out. Okay? In mathematics, we say that this is what we call well-defined. In other words, it's a definition that doesn't work just in certain cases, but it works in every case. Raises and stays on one side works for this one, but it doesn't work on this one. If we really want to define what a tangent line is unambiguously, so people can't argue with us, right? We need a general definition. So here's what we're going to say. We're going to say a tangent line on the graph of some function at a certain point is the line that goes through that point. So notice the first thing you need whenever you're dealing with tangent lines is you need a point on a graph. So here's my point. Right here. A, and this is f of A. This is my point P. And now I need a slope. And so we're going to say that the slope of this line is the slope that we get by looking at the limit of the slope of the secant line is going through the point. That's a mouthful, so let's kind of sketch this out. So here's what we're actually saying. We're saying this. We're saying here's our point. Let's pick another point on the curve. Remember when you had the homework at the point line? You had like this fixed point, right? That was always Q, and then you had another point Q that ended up there. So let's fix our point, look at any other point on the graph, and look at the slope of the secant line. And if that limit exists as x approaches A from either side, then the tangent line exists. This is what we're saying. So we're saying now, if this limit exists from both sides, that's what it means for a limit to exist. It means from both sides when we're looking at a general limit. Then the tangent line exists. At that point. So it's a little backwards. We use the notion of the secant lines and tangent lines to give us a picture for how we're going to get this thing called a derivative. We're going to talk about this in 2.8. Now we're actually saying that the derivative has to exist. Kind of going back and putting a final point on it. So if this is true, if this limit exists, then there's a tangent line it goes through this point. It has this slope, and we know the equation, right? I pick any other point out here on the curve. I'm gonna on this tangent line. I'm gonna call it xy, right? And what do I know? I know that the slope is equal to y minus f of a over x minus a for any point on the tangent line. So I'm using the point slope from the equation alone. And I can just go ahead and rewrite it. Solve for y. You can put it in slope-intercept form, but it's going to turn out that this form is actually useful. We're going to see later on when we talk about polynomial and Taylor series. But this is actually a useful way of writing equations for y. And notice what it says. It says something really nice. It says, okay, when x is equal to a, we start at f of a, and for each increment in x, y goes up by m times the increment in x. This is saying exactly what we know is true for a line. Okay? This is the change in y. As I go from a to x. Alright? Now we're gonna switch gears a little bit. So we have one way of getting the equation we have one way of getting the slope of the tangent. But it turns out we're going to want to use another way. And here's how we think about the other way. Now we still have our point a and f of a, but instead of calling the other point x and f of x, I'm going to say, let's think about this point not as x, but as a plus some distance from a. So this is the point at some distance h from a, so this is the point a plus h. I just evaluate its function. These two points both have to be on the curve. This is f of a plus h. Different way of thinking about it. Now I can set up the slope for the secant line, right? Because this is going to be the point f of a plus h minus f of a. And I really like the bottom because the bottom is a plus h minus a, and that's just h. So this is a different expression for the slope of the secant. And now what am I going to do? Well, as x approaches a, what's that equivalent to? It's equivalent to saying what in this context? As x approaches a, what's happening to the distance between x and a? Decreasing, going to 0, right? And what is this distance? It's h. So, the key here is to notice that x approaches a is the same as a approaching 0. Now I can rewrite this limit, right? This is the limit as h approaches 0 f of a plus h minus f of a over h. So this is a different way of talking about the slope of the secant. And we're going to see this has a lot of meanings. There's reasons why you want to go through all this work and think about this one. If you approach it from below, you can do it in two different ways, okay? Well, we're going to evaluate the limit the same way. Let's go to a different form of the slope of this. Now, if you want to approach it from below, you can do it two different ways. Okay, this is one way you can do it. You say, let's make h negative, and then set up the same sort of thing. Okay, or you can say, let's just let h be h. Okay, I can say let h be greater than 0 and look at a minus h, or just let h be negative and look at a plus h. And either way is fine. Okay, you get the same answer. There's a cool little applet, and I don't think I'm going to be able to. I got it to work this morning. I'm gonna let you play with it. That's what I'm doing, and usually it even tells you it's gonna open. For some reason it's not. And unfortunately I can't, I don't think I can't copy and paste it. Yeah. So I'll leave this to you to kind of play around with. But this is an output that kind of illustrates this. It actually looks at the curve y equal x squared. It starts at 0.11 on the curve. And it picks them up and it tells you what h is. And then you can see what's happening in the secant line with h the same slope, the same thing. All right. So these are our two different pictures. People sometimes call this the average rate of change picture. Sometimes people call it the difference quotient. But the same calculus before we use this call it a difference quotient. But the picture is the same. Instead of x, we just got to be the point we're interested in plus some distance. And as x goes to a, it's the same as saying it's really, these two things are exactly equivalent. It's just another way of expressing it. So let's go ahead. This is the problem that you guys are all experts at, so I won't do it. But let me do it in this form. Let me go ahead and get the equation for the tangent line for the function f of x equals x squared to 0.11. Okay, so this is my function. I'm just going to sketch it out because I know what x squared looks like. Right, 1, 1. And the problem is asking me for the equation of the tangent line. So what do I need? I need two things. What do you think? What do I need for the equation of the tangent line? I need a vertical point. Well, if I have a point on the line, how can I figure out the equation for the line? What else do I need to do? The slope, right? You need to define it. Do I have a point on this line? Sure. Because I'm told that I want the tangent line at this point. This is what this means. So this tells me that I know a point on the curve. So the point on the line is going to be 1, 1. Now I need the slope. That was the easy part. Right, the point. I'm halfway there. So I need the slope. Which I know in this form is going to be the limit as h goes to 0 of f of, now my a is equal to 1, right? 1 plus h minus f of 1, and the bottom's always h. 1 plus h minus 1. So I need to kind of work this out, right? F of 1 plus h, well, f is just x squared. So my m here is going to be the limit as h goes to 0 of 1 plus h squared minus 1 over h. So it's getting to this point. So we asked, like, okay, what are we doing? Is this going to be theoretical? No, it's not theoretical now. We're actually using it, right? We're using this to evaluate the limit. How would I do this? Well, I can do it two ways. I could expand this out, right? And get these to cancel. There's another way I can do this. How it looks like what? It looks like this is 2 squared. Because 1 is 1 squared. So I could also write this like this. I could factor it into 1 plus h plus 1 times 1 plus h minus 1, which is h, all over h. Right. So this is 1 plus h squared minus 1 squared. No matter how you do it, what's going to happen? Well, this guy is going to cancel, and I'm going to get the limit as h goes to 0 of 2 plus h. And how do I evaluate that? Direct substitution. So this is 2. Okay. Now I got my point, I got my slope, I'm pretty much done, right? So my equation for my line is going to be 2 is equal to y minus 1 over x minus 1. And so this should be y is equal to x minus 1. How could I check myself? How could I check myself? I'm making a claim that the line goes to the point 1, 1, right? So when I put y equal to 1 and x equal to 1, I better get it to work out. Is it going to work out? No. Right? So I'm going to substitute. X equal to 1, y equal to 1. And this equation better be true, and it isn't. So I done messed up. This is a good way to check yourself. What did I do wrong? I didn't multiply by 2, right? So that's the right answer. How do I know? I check myself, right? Now I put x equal to 1, y equal to 1. Is 1 equal to 2 times 1 minus 1? Well, even I can do that. That makes sense. It's always a good idea to check yourself. And by the way, suppose, for example, I've got this number wrong. What's going to happen? When I plug that number in, 1 and 1, I'm definitely going to get a wrong answer, right? And it's going to be incorrect. How could I check this value? Well, I have 2 ways of getting the slope, right? Suppose you say, man, I'm really bad at this way. Let me try this way. You can use that way. And you can figure out what the slope is. So there's a lot of different things at your disposal, right? Okay. We're going to pick up here next time. So there's an SI session tonight from 7:30 to 9, 104 COAS. So, you know, if you're not getting it, turn yourself in, okay? All right. Yes, sir.
How did you go to 1 plus h?
Oh, yeah. You know what I did? I did that thing where I factored, right?